Okay. Generally speaking, if you have anything to say, please open your mic and say it. I cannot follow the chat while the screen is in share mode and I very barely see you. And again, I ask you to open your cameras, those who did not do that. I really, really don't care about the entire mess that you may or may not have behind you. Okay, so let's do a quick recap on the things we discussed. So we're going to close down the summary of special relativity today. So what did we do? So we defined the four vectors. We defined the metric, but let's do one at a time. So first we defined uh, we define a four vector V alpha as any quantity whose components transform, like V alpha goes to V alpha prime, which is lambda alpha prime beta, V beta, any quantity whose components transform like that when the coordinates transform the same way. And this is called a contravariant for vector, and the origin of the name, which you know now, is because this transformation law is the opposite to the transformation law of the set of coordinates. This is called a contravariant for vector. This is the precise name, but it is simply called a vector. We stress that a vector belongs to a point. And we gave the example of a tangent vector to a curve. Right? I have a curve in space. At every point on the curve, I can specify a tangent vector to that curve. If this is lambda, then the vector v is just dx mu over d lambda. Right. Then we looked at the transformation law of the set of basis vectors, and we saw that this is the opposite. So we the opposite of a Lorentz transformation is also a Lorentz transformation, but is written with the opposite way, with the first index as a lower index and the second index as an upper index. So um, E prime is lambda nu prime mu E mu transformation law of the set of basis vectors. The opposite, the inverse Lorentz transformation. And then we say that all objects that transform like that, these are called covectors. They have several names. They belong to a different space. That is the cotangent space, which is denoted by Tp prime. And they are denoted with a lower index. So elements of the tangent space Tp star are called covectors. These actually have several names, also called covariant vectors, and also one forms, for reasons which we won't discuss because we simply will not have time. And they are denoted with lower indices, omega mu. And they belong to the dual space, basically, to Tp, which means Tp is the space in which all the vectors belong to. Belong. The set of all vectors form A space TP. So omega mu, and omega that operates on V is just R. Is omega mu, V mu, which belongs to R. We gave a few examples, let row vectors and column vectors, rows and cats, and the gradient. Then we easily generalize that to tensors. We said that a rank, a tensor T of rank KL is a multi-linear map from K dual vectors and L vectors to R. So simply it says that K, it has K upper indices and L lower indices. And the transformation law, just each index separately and the order of the indices maintains. So we don't switch the order. So T mu 1 prime, mu K prime, ni 1 prime, ni L prime is lambda mu 1 prime, mu 1, lambda mu 2 prime, mu 2, lambda mu K prime, mu K, lambda, now the opposite, mu 1 prime, mu 1, lambda nu L prime, nu L times T u1, uk, u1, ul. And then we saw that there was one tensor which we already know about. This is called the metric tensor, eta mu nu. This is a 0,2 tensor. Its operation on two vectors called the inner product. Eta vw is v dot w. This is the inner product. And that enables us also to characterize the vectors. And we said that if eta mu nu v nu v nu. So of course, the norm of a vector is the inner product of a vector with itself. I should write it down also. Eta vv norm of v v squared. And then if eta mu nu v mu v nu can be either smaller than 0, then we say that v mu is time-like. If it's 0, then we say this is a null or light-like. If it's greater than 0, we say it is space-like. We also introduce a few other vectors, such as the Kronecker, which is a 1-1 a few other tensors, excuse me, right? So 1-1 tensor is the Kronecker, delta mu nu. This is the only tensor, the only one that I am writing with the upper exactly above the lower indices, because we cannot get confused here. And so I don't care. Normally, I would never write any tensor with any index exactly above. There is always a space for each index. We introduce the inverse metric, eta mu nu. This is the inverse metric. This is a type 2-0 tensor. We introduce the Levi-Civita tensor. This is 0,4 tensor. Epsilon mu nu rho sigma. Then we spoke a little bit about manipulating tensors. So we said I can use the metric and the inverse. These are the only tensors I can use to raise and lower indices. So if I have T alpha, so we said raising and lowering indices, said I can use the metric and the inverse metric. So T alpha, beta, gamma, delta. If I multiply by eta, whatever, mu gamma, then I just take the gamma and I raise it. I'm going to get T, alpha, beta, mu, delta. Note very importantly that the location and the other indices, they don't change. I don't switch the order of the indices. That's very, very important. Okay? Then, so for example, I can use the metric to turn a vector into a covector and vice versa. V mu is eta mu nu, V nu. Omega mu is eta mu nu, omega nu. Right? I can do a contraction. One thing. The second thing is a contraction. As mu rho sigma is T mu nu rho sigma nu. Right? I can contract two indices. Always, one is an upper, one is a lower. That pretty much is sufficient to give us the necessary mathematical background to start. And then we switch to physics and we spoke about special relativity kinematics. But we say that in special relativity, it makes more sense to speak of a word line. So we took in all the spatial dimensions, we squeeze into one. So that will be the x, with an x vector, and the time would be the horizontal axis, ct. And then I can speak of my word line. A line that specifies what is my location, what is the location of each particle or each object of interest at space and time. Of course, this is a curve, which is specified by some parameter. I can choose, this is called the word line. It should be a little bit more fun and do that with color or whatever. But you got the idea. Now I can select every parameter to parameterize where I am on that word line, but there is only one natural parameter, which is the proper time, tau. So I write down the location of each object as x mu is x mu as a function of tau. For a given tau, I know where I am. Having that, then it's straightforward to define other four vectors relevant for physics. Now I switch gear from talking purely about math to talking about physics, right? So now I can do the derivative with respect to tau, and I can define the forward velocity. U mu is dx mu over d tau. And straightforward to show that if I look at components, then U0 is just gamma C and Ui is gamma Vi or gamma beta IC. That's what you're familiar with. The norm is a negative. U squared is minus C squared, which means that U is a time-like vector. Then the second vector that I can introduce, or the third vector, right, it would be the for acceleration. A mu is d u mu over d tau. And the fourth one would be the for force, F mu, which is m a mu, or m du mu, u capital mu over d tau. And that really replaces Newton's second law. And I said that if you do the math, you realize that the acceleration is always perpendicular to the velocity. So a mu u mu is 0. It shouldn't bother you, right? Because that simply means we have four equations here, right? We have four components of a and u. So there's one equation with four components. Simply means that one of the components is dependent on the other three. That's all. So I should not get too alarmed. Then we introduced the fifth vector was the 4 momentum. P mu, which we define as m dx mu over d tau, is m u mu. And using what we derive for the 4 velocity, we see immediately that the norm is minus m squared c squared. And components P0 is gamma MC and Pi is gamma beta I MC. And then we saw that in the limit where V is much smaller than C, that means that beta I is much smaller than 1. Then we got that P0 is MC plus 1/2 M V squared over C, and Pi is just MVI. And so here we just take that and we multiply by C, and we get that C P0 is mc squared plus 1/2 mv squared. And this was identified as the kinetic energy. And therefore, Einstein identified this term as a rest mass energy. It simply fell out of the equations right away. Didn't need to do anything. Just need to write down the equations properly. Now, I don't know if you're aware of, there is a very nice historical debate, which was back in the late 19th century, about what is the age of the Earth. Have you heard about that? It's a very nice story between one of the leading top physicists of the time, Lord Kelvin, the same Kelvin from the temperatures, and somebody who was not a physicist at all, but still possibly the top scientist of all times, which is Charles Darwin. And the question was, how old is the Earth? And Kelvin calculated to be something like 30 million years or something like that. That was based on the amount of energy available in the sun. He knew to calculate what is the flux of energy that flows from the sun. And he could know what is the mass of the sun. He calculated how long it will take before the sun exhausted all its source of energy. Darwin knew nothing about physics, but of course he knew biology, or at least he got a very, very good intuition. And he looked at glaciers' motion and the valleys, and he concluded that in order to produce the valleys due to glaciers, it must have been way longer than 30 million years. But of course, he had no way of proving it. This was, of course, solved by Einstein because of this term, right, that Kelvin had no way of knowing about, and he couldn't imagine it, and this is the true source of the energy of the sun. Right, conversion of mass into radiation, and that contains a huge amount of energy. And today we know that the sun is active for about 4.5 billion years, more than about 3,000, more than how much? More than 1,000 times more than what, more than 100 times more than what Kelvin calculated, based on his knowledge. So at the end of the day, Darwin was right in that too. Now, because of that, just to finish, right, because of that, CP0 really represents an energy of the particle. This is the particle's energy. And because of that, the P mu is also known as the energy momentum. Or vector. And using these results, using that result here, we can write down that P0, which is E over C, is just Pi squared plus M squared C squared to the power 1/2, which is known as the Einstein's energy relation. I think this is as far as we managed to go through on Thursday. So before we proceed, I'd like to stop here and ask if any of you have any questions. Any questions, anybody? No? No, that means that everything is clear. You're mastering special relativity. Any questions in special relativity that may or may not appear in the exam, you will know how to answer with no questions. That's what it means if you have no questions now. You sure? Okay. So we still need to do a few more things to wrap up the discussion about special relativity before we can move on. So one thing which we haven't touched, so let's do it briefly, it's called massless particles. So everything we did so far, of course, contain particles that have mass, right? M is greater than 0. And therefore, they are obliged to move at velocities which is less than c. What about massless particles? Really, it's photons, right? These are photons. Neutrinos do have masses, although very small, but we're talking about photons. So what photons, of course, have to travel the speed of light, see? Photons travel at c, so x is equal to ct. What does it mean? If you want to specify a photon world line, can I use tau?
No,
Why not?
because it won't experience time.
Exactly, right? I don't know if you thought of that, right? I mean, what is the distance from the sun to the earth?
One astronomical unit is 1.5.
In kilometers, actually, in light years, light minutes. How
Eight,
long?
8 minutes.
8 minutes, right? So it takes a light from the sun, photon once it's emitted from the sun to reach our eyes, something like 8 minutes. But let's say that you are a small dwarf that sits on the photon. So from the photon's perspective, how long it takes the photon from the moment it's emitted to the moment it is reaching Earth or reaching our eyes?
0.
0, right? I don't know if you thought of that, right? But from a photon's perspective, it's exactly 0 time from emission to absorption or detection, whichever way you want to call it, right? So you can't really use the tau for that because the tau is always 0. To describe photons world line, we cannot use d tau because d tau is equal to 0. So we must choose a different parameter. You can call it whatever you want, call it lambda. And then we can say that mu is dx mu over d lambda. Lambda is just parameter. Of course, the forward velocity is a null vector. The u squared is equal to 0. And if there are no forces, of course, there is no acceleration. Du over d lambda is equal to 0. Right, so this is photon's equation of motion. What about the photon's energy? Of course, it's an internal property that relates to its frequency, angular frequency, E equal h omega, h bar omega, right, or h n. That, by the way, Einstein himself found, right? This is Planck's constant. And if we put m equal to 0 here, right, that means that the momentum of the photon pi is, that's photons energy. And photons momentum is just E over C, which is h bar k, where k is the wave vector. This is the photon momentum. So overall, we have P mu is just h bar omega over C and h bar k. And P squared is equal 0. That's nice and easy. All right? Fine? Okay, this I believe you've seen, right? I didn't tell you anything new. But now we do need to say something which is new to you, because this is something which we are going to make a wide use in the future. So far, I believe that all that, right? The kinematics part of special relativity you have seen one way or the other in introduction, modern ideas, or I don't know how you call this course, right? Am I correct?
Yes.
Yes. Okay. But now things which I believe you haven't seen. So far, everything we discussed considered a single particle. Massive, massless, we don't care, right? It's a single particle. But in life is a little bit more complicated than a single particle, and the universe contains more than a single particle. So we need to look at many particle systems. And for that, we have to introduce a new tensor, which is called the energy momentum tensor. Another name is called the stress energy tensor. So let's write it down. Many particle system called the energy momentum tensor. It's not the energy momentum 4 vector. Now, place that you were supposed to see that is in classical fields, whatever. You call it maybe in fluids, possibly even in solid state. Did any of you ever encounter the concept of tensors before this course?
In fields, electromagnetic fields.
Electromagnetic fields.
Yes.
Who said that?
Me.
Say it again. Me, okay. What tensor did you see that? There?
I think that the energy momentum.
Okay, that's where you're supposed to see that, so I'm quite glad, because for some reason it was not shown there. So now let's do it in an ordered way to make sure that everyone is aligned. So the energy momentum tensor is a symmetric. This is a 2-0 tensor that basically tells us everything we need to know about the energy aspects of the system, namely the energy density, the pressure, the stress, etc. In case you were not sure, pressure is the same as energy density. They carry the same units. Check it out. So it's called T mu nu. That's a standard notation. And what it says is basically, very roughly speaking, this is the flux of the form momentum P mu across a surface of constant x nu. Just write it down to give you the idea. The flux of form momentum P mu across a surface of constant x nu. So to get the feeling of what it means, we need to introduce the concept of a fluid, which is essentially a continuum of matter which is described by macroscopic quantities, such as temperature, pressure, entropy, etc. Now, but fluid is a little bit too general to our purposes, and it's a bit more complicated. So this you'll learn if you take a course in fluid dynamics. What we actually are interested in is what's called a perfect fluid. So for I should just say fluid is a continuum of matter described by macroscopic quantities that you learn from thermodynamics: temperature, pressure, density, rho, n, entropy, S, viscosity, etc. Now, what we are interested in is not a fluid in general because it's too general and we don't really need that. So we're interested in what's called a perfect fluid. In fact, nearly everything you find in astrophysics falls into this category of a perfect fluid. So, electromagnetic fields, stars, universe, interior of the sun, everything can be thought of as a perfect fluid. So what's a perfect fluid? There are various definitions which you'll find in various textbooks, and it turns out they're all the same. So, for example, I wrote down that the textbook by Schultz defined a perfect fluid as a fluid with no heat conduction and no viscosity. No heat conduction, no viscosity. Weinberg says that it's isotropic in its rest frame. Right, so for me, think of yourself sailing down in the ocean and you look around yourself and everything looks the same. This is some sort of a perfect fluid, of course, in the 2D. It can be shown mathematically that these two definitions are in fact identical. So it's not, it doesn't matter. From our perspective, we can say that the perfect fluid is fully characterized by only two parameters, which are the pressure and density. So fully characterized by pressure and density. And that's it. Have you encountered fluids before? Well, this is the first time that you're seeing that.
Is a fluid like an ensemble in statistical mechanics?
In a way, but right now we're talking about physics, not about mathematics. So you know what, let's start to discuss it and you'll see what I mean. So the first two, before we get into general fluids, let's speak about a specific fluid, which is much simpler, and we call it dust. This is a good timing, right? We're just before Passover. Many people are interested in dust and how to get rid of dust. So what is a dust? How do I define a dust? I think many of you might have been busy with dealing with dust in the last few days or will be busy in the next few days. So what is a dust?
Small particles.
So yeah, well, fluid is also made of small particles, right? If I'm thinking of a glass of water, there's water, the water is small particles. So what's the unique of these small particles that I call them dust?
They don't move. They rest.
Right, right. They don't interact with each other, right? So I can simply think of a dust as a collection of particles that just lies there, right? So in reality or mathematically, I can say that a collection of particles at rest with respect to each other. Or I can think of them as a perfect fluid with zero pressure. The particles don't touch each other, they don't care about each other, so they don't put any pressure on each other. Right? Or perfect fluid with zero pressure. Now, of course, they all have equal velocity in any fixed frame. Then we can imagine of something like a 4-velocity field. Right? 4-velocity field, u mu, which is defined over all space-time, right? So if I take the dust, right, they're all moving at the same way relative to me, all the dust particles, right? So the 4-velocity field is defined over the entire space-time. So now I can define what's called the number flux. Define number flux for vector. And mu, this is n u mu. N is, of course, the density. N is the density of particles in the rest frame. Right? Again, so if I'm looking at the dust, which is not moving, so the rest frame, I just have a density of particles. They don't touch each other, but I'm interested in any frame, right? So now I'm looking for some arbitrary frame. So in arbitrary frame, N0 is the number density. So then I speak of number density to discriminate from energy density, right? So this is the density of the particles when I count them one by one. I can think of number density, mass density, energy density, various density. So when I say density, right, per unit volume, that's what it means. Don't get confused. So the same, I remember I was confused initially as a student with that. So, there is when I say density, it just means that I take the quantity and divide by the volume. So it can be the number by the volume, it can be mass by the volume, it can be energy by the volume, it can be many things. And Ni, so N0 is the number density. Ni is the flux of particles in the xi direction. Right? If I'm in a frame in which all the dust is moving, I'll be moving towards the dust, right, at some velocity, then I'm seeing them moving to me, so they're crossing a surface at a certain rate. That's the flux. Of course, in the frame in which they're at rest, the number flux for vector what is the number flux for vector in the frame where they're at rest? I just define it here.
0?
No. What's the zeroth component of the number flux?
The number of the particles.
Right. And the x component, y and z components?
0, 0, 0, no?
Right. Right? That's it. That's at rest. Right? This is a frame in which they're all at rest. Now, of course, without loss of generality, I assume that all the particles have the same mass m. Particle mass So in the rest frame, the energy density in the rest frame. Before I spoke of the number density, but what is the energy density? I denoted with a row to discriminate with n, the number density. If I just say, okay, I have a number n of particles, what would be their energy in the rest frame?
nmc squared.
Right, exactly. So this is the number density. It's just n m c squared. Right? They're not moving. Now we said that there is zero pressure. And we said that perfect fluid is only described by two quantities, energy density and pressure. So energy density fully specifies everything we can say about the dust. But what we care about is not only what happens in the rest frame, but in any frame in which they may be seen to be moving. Right? If I'm now an observer that is moving towards the dust with some broom, so I want to sweep the dust, I want to know what is the how to specify the dust. So I can realize that both the density mc square can be zeroth component of four vectors, right? So remember we had n mu is n 0, 0, 0, right? P nu is mc 0, 0, 0, right? So we can think of rho in that interpretation, you can say, right? We can think of rho as the 0, 0 component of a more general tensor, which measures which is measured in the dust rest frame. So this leads to define the energy momentum tensor of dust. T mu nu of dust is P mu and nu, or N M U mu U nu, or rho U mu U nu. Rho is the energy density in the rest frame. This enables me to generalize the discussion or the quantification of dust to any frame, not necessarily a frame in which it is at rest.
Couldn't you divide by c squared?
Yeah, I put C to 1.
Okay.
Now, as a side, add up your relevant quantities of C. As a side, right, I can write down the conservation laws of particle number in a very elegant way using the gradient. So, conservation law of particle number. I simply write it down as d mu n mu is equal to d n mu over dx mu is equal to 0. Which is a very elegant way, because if I start now to express this using what we saw earlier, right? What is u0 is gamma c and ui is gamma beta ic. You'll find out that what is really written here is the zeros component is d gamma n over dt plus d gamma NV over dx is equal to 0, which is just d gamma n over dt plus nabla gamma NV is equal to 0. And this is the relativistic generalization of the continuity equation. If I multiply that by current, sorry, by charge, then I get conservation of current. Have you seen, just to make sure that I'm not talking to myself, have you seen a continuity equation in the past?
Yes.
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 Yes, not in this form.
Not in this form, but in this form, without the gamma, I have seen.
Yeah. Yes.
Yeah, okay. So this is the relativistic generalization of it. Just quite cool, right? Sometimes you're gonna, well, I won't have really time to show you that, but many of the equations that you're familiar with, you can write in a very, very compact form using these notations, and also this is relativistic generalization. Specifically, this goes to Maxwell's equations, which I actually have it in my lecture notes, but I won't have time because we have a short semester. I won't go through that because we don't need it for this course. So I will put it, I'll post my lecture notes on special relativity on the course webpage today. You can have a look at them, of course. And there is some, at the end, I write down how to write down Maxwell's equation in a compact form. I won't go over that in class because, again, we don't have time and we don't need that for the rest of this course. Okay, but let's finish first. So this was dust. Now let's generalize that to fluids. Again, perfect fluids. So we said perfect fluid. So perfect fluids, we said one definition is that they are isotropic in their rest frame. If they're isotropic, that means that there is no flux, no preferred flux in one direction. So that means that T mu nu has to be diagonal. No preferred direction of flux flow. Means that T mu nu is diagonal. And also that means, since we don't care which direction it is, it means that all the diagonal terms has to be the same. And T11 is equal to T22 is equal to T33. So really we have only two independent quantities. Which are T00 and TII. So we could arbitrarily select this one to be rho to be consistent with the dust case, and this one we can put a P, but now it's a pressure, of course. Right? If I don't put an index, that means a pressure, not a momentum. Then we can try T mu nu is equal rho P P P. Actually, this is the right. Let's try. This is the true. This is true in a rest frame, in its rest frame. But what about any frame? So for dust, general frame. For dust, we had T mu nu is rho u mu u nu. So we can try generalizing that to add up the pressure, so that rho plus p u mu u nu. But then, of course, in the rest frame, where u mu and u nu are just 1 0 0 0, this would lead to rho plus p 0 0 0, and then everything else is 0. So we must add something that looks like minus p plus p plus p plus p. But how do we write this term?
P times the metric.
Exactly. So this is just p times eta mu nu. Very good. So the general form of the energy momentum tensor is also known as the stress energy tensor. T mu nu is rho plus p u mu u nu plus p eta mu nu. Again, this is also known as stress energy tensor. You said it, at least some of you said that you have seen that before in the MM. Am I right?
Yeah, I have.
You have? Okay, well, at least one have. What about the rest?
No, what's the stress mean in this sentence?
Again, I did not fully understand what you said. You have seen it or not?
No,
No.
so what's the meaning of stress here?
Okay, so you see it here for the first time. That's fine. It's very important that you see that what I wanted to say that it does not appear only in the context of general relativity. Of course, I introduce it here because I need it, right? You put a gun in the first scene, and we're going to use it down the line. So I have to introduce it here. But it is useful in many other branches of physics. So that's why it's likely that you were or you should have, or maybe you will in the future encounter it, even if you're not doing astrophysics. If you're doing other branches of physics, you may also see that. What is the meaning of the stress energy tensor? I see in the chat. As I said, the stress energy tensor essentially tells us what is the all the energy and momentum aspects of a system, of a continuous system. Now we're not talking about a single particle. We're talking about a fluid. So this is an ensemble of particles that have pressure and have energy density. Again, in astrophysics, everything is a perfect fluid. You can think of stars in the galaxy as perfect fluid, in a way. You can think of the universe as a whole made of flowing gas as a perfect fluid. You can think of the solar interior, even the Earth's interior, as a perfect fluid. You can think of electromagnetic radiation as a perfect fluid. Okay, and this simply tells you what is the flux of momentum through each boundary. Okay, in solid state physics, that would correspond to deformation of solids.
Well, why is it being used the term stress?
Why is it being used for what?
Why the term stress is being used for that?
Stress
that
is being used. Stress is being used when we talk about solids. In fluids, we don't have stress, so that's why it's called energy momentum. In solids, there is stress, so that's why it's called the stress energy. Okay. The most important thing about it, it's also answering your question, is that it is conserved. Namely, stress energy tensor is conserved, so it really expresses any tensor is conserved in the sense that d mu t mu nu is equal to 0. So the gradient is 0. And what is written here, how many equations are there? How many equations did I just write? How many?
60.
No. How many equations are there here?
4.
4 equations, right? So I have 4 equations. So nu equal to 0. This is really conservation of energy. D mu T mu 0 is equal to 0. And the ith component, D mu T mu I is equal to 1, 2, 3, right? This is conservation of the ith component of the momentum. Pi. Again, once you get used to it, this is what's called Euler's equation, if you encounter that. If not, this is just a very, very strong way of describing conservation of energy and momentum. Essentially, this is what it is. All right. I'll give you a problem set to play a little bit with that, at least get the feeling of understanding. But then again, as I said, you have 2 weeks now, at least 2 weeks of Passover holiday. Use the time to go over and review the material and maybe go to the textbook about problem sets. There are plenty of problem sets about energy momentum tensor. It is very, very central to physics. So it's not something that maybe this is the first time you see it. I don't know, but this is certainly not the last time you're going to see it if you continue to be a physicist. All right. This pretty much concludes what I wanted to tell you about special relativity. Believe it or not, you have all the tools needed to solve all the problems that you have ever seen in special relativity. So I urge you to go and practice it. Mathematically, you don't need anything more than that. And physically, we covered pretty much all that needed. You see that the physics got quite easy after we went through the math. And now I want to go to the next step. We're still not going to do any heavy math now, but we're going to go through the next logical step that leads us to general relativity. And the next logical step is called the principle of equivalence. And its consequences. Special relativity, generalizes classical Newtonian physics into the realm where velocities get close to the speed of light. But there is still no notion of gravity here, right? We have not attempted to do anything related to gravity. Now is the time to start thinking of that. And really the discussion is going to divide into two. So I mentioned that in the introductory lecture, the true ingenuity of Einstein was that he gave gravity, which is a physical force, a geometrical interpretation. Namely, that the interpretation is that the space-time is not flat, is not Euclidean, and not even Minkowskian, but is curved somehow. We still need to fully understand what does it mean curved, how do we describe curved spaces, and of course, how is all that related to physics, which it is. And the answer to that essentially is given by Einstein. This is the famous paper from 1916, where he introduces Einstein's field equation, which essentially tells us how the existence of matter acts to curve space-time. And the answer is given by Einstein's field equation. And we're going to spend a large part of the semester building the tools that enable us to understand this equation and what it is and how to derive it. And then the second half of the semester will be to solve it in simple cases. The second question is, now assume that we're accepting that interpretation, that the space-time is curved. How do particles travel in such curved space-time in such a way that we, as observers, we call their trajectories, we see that they are being bent relative to flat space-time, and we call this bending as due to gravity, right? It turns out that this is a much simpler question to answer, so we're actually going to start answering this question first, because it requires much less math and slightly more insight, but let's write it down. So how do particles, when I say particles, I also include massless particles, namely photons, travel in curved space-time such that their trajectories are being influenced by gravity. So as I mentioned, in fact, answering the second question is much easier and more intuitive to understand than answering the first one. So we're going to start with the second one. And for that, we need to call for help the equivalence principle. What is the equivalence principle?
The speed of light is measured the same in all internal frames.
No, that's not the equivalence principle.
You can refer to when well the thing and it's so relation if I can't see what's around.
I'm not sure. Again, can you repeat, please?
That you can't differ between a love everything and acceleration.
Yes,
without
yes,
changing
yes.
your surrounding.
Yes, you're right. Very good. The equivalence principle is Iltvosh's experiment, essentially, right? Remember we spoke about that? Iltvosh, which I asked you to read about, right? He says that mi, inertial mass, is equal gravitational mass. Namely, mi is mg. This is, in fact, so important that it has its own name. This is called the weak equivalence principle.
What's the strong one? Is there a strong one?
This means, remember, that we also discussed that in the Einstein's thought experiment, saying that if there are physicists that are in a freely falling closed elevator, they cannot measure gravity, right? That means that there is no way to disentangle the effect of gravitational field from those from being in a uniformly accelerated frame. Remember, this is only true for gravity, because if we talk about electromagnetic forces, then the coupling constant, right, to the electromagnetic field, Q, the charge, is different than the inertial mass. Right? So we can think of mg as the equivalent of the gravitational charge.
But shouldn't that be true only for first order?
Yes, of course, because let's say we're looking at this elevator experiment, right? We have two physicists, right? And they are in an elevator which is freely falling, right? Of course, they have no way of measuring gravity if they're freely falling, right? But actually, they do have a way, which is a second order. Why is that? Let's say it was a very... What?
Can I answer? I
Yes,
think I
please.
know the answer. Because at second order, like the field lines are not exactly parallel, so
Exactly.
gravity is not flat.
Exactly, right? If this is Earth, right, they are all both attracted to the center of Earth, right? So if I'm looking at their, gravity, they're not exactly parallel to each other, right? And so, if they wait long enough, they could measure that they're slightly getting closer to each other. Of course, this is a very small effect, but on a small distance, it's a small effect. If it's a large distance, right? If one of them was here and one was in Australia, of course, they could easily tell that they are moving in different directions, right? So that's you're right, that this is we have to limit the discussion to a small enough region in space, right? This is true in a small enough region in space-time. Right? Because for a big enough elevator, then the gravitational field would slightly change from one look. Of course, the gravitational field slightly changes from one location to another inside the elevator. So if the elevator is sufficiently big, then they should, in principle, be able to measure it. Right.
I have a question.
Yes.
So obviously Earth is not a smooth manifold, but this even works in manifolds?
Yes, of course it does.
Okay.
When we say small small, does we mean that locally we can think of the alphas as a flat flat.
Yes, locally flat. Yes, exactly. That's what it means. How small, of course, that depends on the strength of the gravitational field, etc. So I cannot specify exactly how small, but locally. Okay. So of course we have to have I have to add here in a small enough region of space-time. Motivated by that, Einstein postulated what is known as the strong equivalent principle, which states the following. At every point in arbitrary gravitational field, it's possible to choose a locally inertial coordinate system such that within a sufficiently small region of a given point, the laws of nature take the same form as in an accelerated Cartesian coordinate system. This is the strong equivalence principle. What is Einstein really telling us? So the following, look, I don't care what gravitational field we have. Every location in every arbitrary gravitational field, I can always find a freely falling coordinate system, which is true locally. I don't know what is the distribution of masses. Remember, we spoke about that in Newton's bucket experiment. Right? There is always, everywhere in space or space-time, I can always find a locally inertial coordinate system in which the laws of special relativity hold. So everything we learned about special relativity in the last few lectures, they're okay. They hold. We don't have to throw any of them away.
So the difference between the weak one and the strong one is the locally.
No, the difference is the weak one is the experimental test of Oshkosh that shows the equivalence of gravitational mass and inertial mass. The strong one is the Einstein postulation that in any arbitrary gravitational field, in any point, doesn't matter where I am, there always exists a freely falling frame. And a freely falling frame in which I cannot measure the gravity locally because it's freely falling. And in this freely falling frame, all the laws of special relativity hold. No gravity. I don't need any gravity. Alternative. Of course, this is locally because the gravitational field is not homogeneous. If it was homogeneous, I could think of it as being global. But since it's not homogeneous, it varies from point to point in space, then I can only think of it as being a local freely falling. Alternative. Again, you're now sitting in your home, right, next to your computer, and you don't flow in the air, right, because of gravity. You feel the force of gravity. But instead of, because you're now subject to the Earth's gravity, right? This is your home. And you're subject to Earth's gravity. Now, instead of that, you might be right now inside a spaceship that accelerates at acceleration a, which is equal to g. And this claim, Einstein's strong equivalence principle, says that you will feel exactly the same. You wouldn't notice. If you don't look outside of the window and see anything that is changing relative to you, you could not tell that you're not sitting down in your home right now. Any physical measurement that you do would give you exactly the same outcome. There is a question here about what we call Gaussian normal coordinates. I have not called anything a Gaussian normal coordinates. I'm not going to, since this is a very, very mathematical course, I'm only going through, I define everything I use. Believe me, if you catch me in something that I'm using that I haven't defined, you stop me. It's not going to happen. I'm not going to, everything that I'm going to use is I'm going to define it. It's crucial in this course. I have not defined anything that's a Gaussian normal coordinates. I'm using Cartesian coordinates and I can use spherical coordinates, but this is in the standard meaning as you're familiar with. I'm not inventing here anything. And I'm not talking about any, what the equivalent principle is stating, wherever I am, in any arbitrary gravitational field, there is always a freely falling coordinate system local. It will not be the same here in Australia, right? So if this is Earth, right, and we are here somewhere, and this is Australia, and down there somewhere, right? I don't know, whatever. Then there is always here a freely falling. Think of it like you're a freely falling paratrooper, right? You'd like to be a paratrooper, so you're jumping off the airplane, and you don't feel gravity for a few seconds or a few minutes, right? And if there is somebody in Australia that is doing the same thing, then they will also have a local freely falling coordinate system. Of course, their system, your system going in this direction, their system will go in that direction. So it's not globally the same. But locally, there's no problem. Right. Now, this is the strong equivalent principle. And I have a few more minutes and I want to use them because this is by itself enough to give us already an observational effect. So I'm going to use the last few minutes of this class to tell you about that. This is called the gravitational redshift. don't get confused. In this course, we're going to learn about two separate sources of redshift. One is called the cosmological redshift, which is due to the fact that the universe expands. We will talk about that towards the end of the semester. And the second is what we're doing now, which is called the gravitational redshift, which is a direct consequence of the equivalence principle. Okay? And it goes like that. We are here. And let's say we have two people. One of them is on a ladder. So, classically it's Alice and Bob. Since we're in Israel, then let's call them Ayala and Benny. And Ayala is standing on a ladder because she needs to change the bulb. And Benny is standing at the bottom of the ladder. And of course, the ladder has a height h over the ground. Okay, this is Ayala. This is Benny. And of course, they are on the Earth, so they feel gravity, G, both of them. Right? Now Ayala wants to tell something to Benny. Give me the bulb, whatever. She wants to transmit a message to him. Right? What does she do? Well, the only thing she can do, she sends him a photon. And then she sends him a second photon. And the two photons she emits are separated by time, delta tau Ayala. Of course, this is measured in her local clock, local frame. And Benny receives the two signals at time separation, delta tau Benny. Now I argue that always delta tau Benny is smaller than delta tau Ayala. Always. How can that be? This is a direct consequence of the weak equivalence principle. Namely, instead of both of them being subject to the gravity, I can think of both of them as being inside a spaceship that is accelerated. At acceleration a, which is equal to g. And because of that, when Benny receives the signal, he's moving slightly faster because of that acceleration than when Ayala was when she was emitting the signal. Okay. Let's see how it works. We're gonna do like a first order effect. We're not gonna use any second order effects here, right? Only first order. So we're going to throw up terms. So ignore terms of V over C squared. We don't care about them right now. So everything is going to be classical Newtonian, and everything is going to be good to GH over C squared. So this would be the z-axis. Right? Z-axis. So the position, since everything is accelerating, due to the acceleration, Benny's position in the z-axis, Z Benny. What is that? There is an acceleration forward, right? At acceleration g. So what is the position of Benny in accelerated since he's like an accelerating spaceship at time t? Yeah, guys.
VT.
Is
Well, he is accelerating, so AT squared.
half, right?
Yeah.
Half GT squared. Guys, this is something that I wake you up at 4 a.m. because of an alarm, then you know, right? So if you don't know that, we have a serious problem right now. Half GT squared, right? What is Ayala's position? Z Ayala?
H.
Half GT square plus H.
Half GT squared plus H. Now remember, when we speak about special relativity, we always speak about events. So the first event is that Ayala sends the first photon, right? That without loss of generality, this can happen at t equal to 0. And the second event is that Benny receives the first photon. This happens at t1. So the distance traveled by photon 1 is Z Ayala at t equal to 0 minus Z Benny at t1, right? And the photon, of course, travels at the speed of light. So this is C t1 if it travels t1. But, right? That's clear to everybody? So t equal to 0, Ayala sends photon 1. T equal t1, Benny receives photon 1. So what is Z Ayala at t equal to 0?
H.
H. And Z Benny at t1?
Benny at T1, half G.
Half G t1 squared. This is equal to C t1. Now, this is the first equation we have. Now for the second photon. Ayala emits the first photon at t equal delta t Ayala. Second photon emitted. Benny receives the second photon, the time, delta t Benny, after he receives the first photon. So t equal t1 plus delta tau Benny, second photon received. So what is the distance traveled by the second photon? Okay. Z Ayala at delta tau Ayala minus Z Benny at T1 plus delta tau Benny is equal what? C times how long was the photon in motion? Time it was received, T1 plus delta tau Benny minus time it was emitted, delta tau Ayala. Yeah? You are too quiet for this type of problem.
It's very simple, though.
It is very simple, yes.
We're looking for the catch.
Are you looking for the catch? Well, there is no, I told you what the catch is. The catch is that as opposed to what you counterintuitively may think, delta tau Benny is not the same as delta tau Ayala.
Yeah.
So Z Ayala at delta tau Ayala is H plus half G delta tau Ayala squared. Z Benny at time T1 plus delta tau Benny is minus 1/2 T1 plus delta tau Benny squared is equal whatever is written here. So I'm going to expand that. I have H plus, sorry, I have here minus 1/2 G T1 squared minus G T1 delta tau Benny. I expanded these two plus 1/2 G delta tau Ayala squared minus delta tau Benny squared is equal what is written here. Since this is a second order in delta tau, then I'm going to remove that. And I'm left with H minus 1/2 G T1 squared minus G T1 delta tau Benny is approximately equal C times T1 plus delta tau Benny minus delta tau Ayala. H minus. Right? Now we have this equation. So I'm going to subtract it from this equation here. And I'm left with minus G T1 delta tau Benny is approximately, CT1 is gone, is C delta tau Benny minus delta tau Ayala. But T1, right? T1 is approximately, again, H over C. T1 is approximately H over C. It's all for first order. So we have delta tau Benny is delta tau Ayala 1 over 1 plus G H over C squared. Or if I'm looking at it as a Taylor expansion, this is delta tau Ayala times 1 minus GH over C squared. This is all first order approximation. Remember, delta tau Benny, this is the interval between the recipients of the two photons by Benny. Delta tau Ayala is the interval between the emission of these two photons by Ayala. And as we see from here, right, this one is shorter.
I have a question.
Wait, the equivalence principle says that this is exactly what's going to happen in a gravitational field. I'll just finish, since GH is the difference in gravitational potential, right? GH is first order, this is delta phi. Then we can write down delta tau Benny is delta tau Ayala 1 minus delta phi over C squared. So when the receiver Benny is deeper, is lower in the gravitational potential, right? Then the signal will be received quicker. And of course, the opposite is true. If the receiver is upper, outside of the gravitational potential, then the signal will be received slower. Now, this is experimental fact that was tested first in the 1950s. That's 1959. This is the Pound-Webka experiment. I don't know if you heard about that. They did it in Harvard. One of them in the 1950s, the experimental facilities were good enough so that they can actually measure it. One simply go on the top of a tower, one went down to the bottom, and they just sent signals to each other and they actually measured it. That's called the Pound-Webka experiment. Now, similarly, just let me finish that, and I'll take questions. Right? If we look at the frequency, this is Pound-Webka experiment. This is one of the first experimental tests of general relativity. Now, since the frequency nu of light goes as delta t, delta tau minus 1, you can think of it as, you know, the time between two crests of light. Then if a light, and the light is emitted at frequency nu star, a light from a star is emitted at frequency nu star from the surface, from its surface. It is observed at different frequency, right? Nu infinity is nu star 1 minus delta phi over c squared, which is nu star 1 minus gm over r c squared. M, of course, is the mass of the sun, and r is the is its radius. Of course, nu observed, nu infinity, is smaller than nu emitted, which means that the wavelength increases. Lambda is c over ni increases, meaning that this goes through the red part of the spectrum. That's why it's called redshift. I just make a small table of various objects. So for example, the Earth, the radius of the Earth in centimeters is 6 times 10 to the 8. The mass of the Earth in grams is 6 times 27 grams. And therefore, gm over r c squared. Of course, g and c squared are constants. This is of the order of 10 to the minus 9. Looks very, very small, but it has one very important consequence. Where do we see that today?
GPS, maybe.
GPS. Right. Today, pretty much each of us carries a small GPS with it. If we didn't take that into account, the GPS would stop being accurate within a few hours. Pretty sure Einstein did not think of GPS, but there we go. Sun is 10 to the 11 centimeters. Radius mass is about 10 to the 33 grams, and then gm over rc squared is 10 to the minus 6. Small, but important enough to be seen. Stars which are called white dwarfs have much smaller radius and similar masses to that of the sun, and their gravitational potential is 10 to the minus 4. And finally, neutron stars, the most compact objects that still exist without black holes, is radius is 10 to the 6, the same mass roughly as the sun. The gm over rc squared is around 10%. And this is very notably seen when people are doing spectroscopy to try to get what the elements are in these stars. Now questions. Somebody had a question. Please go and ask.
Okay, so I wanted to ask, so proper time can be different. Proper time can be different if there are two observers experiencing the same acceleration, but their position is different along the axis of acceleration. So this example, it was the z-axis, the position was different. So is that correct?
Yes.
And that is regardless of their velocity to each other.
Right, because now we're talking about gravity, which is so another way of thinking of it. When you're moving from within a gravitational potential, right? What we really have here is a potential well, right? And when we're moving from different locations inside the gravitational well, then yes, it's different proper time. So the proper time is local. That's also why it's called a proper. It is true
Okay.
to me. My clock is true to me. It is not going to be the same clock as yours. Yes, so this is one of the, this is a bit confusing, yeah, because we're not talking about the time, we're talking about proper time. So my proper time depends on, actually, no, my proper time is proper time, it goes with me. But the difference between us, what happens really here is that the photons travel into different locations inside the potential well. Right?
Mhm.
So they're changing their proper time, basically. You can think of it like that. That gives various effects, and the simplest one of them is this gravitational potential, which we just introduced to first order. Of course, we'll have a more thorough discussion of that down the line.
But why is that so if the photons aren't accelerating?
The photons are not decelerating.
Yeah,
They're
they're not. So they.
Their energy changes. And again, this is a direct consequence of the equivalence principle, of the fact that when you're in a different locations inside the gravitational field, you can think of it as being in the different accelerated regions. As we said, I mean, go back into the example, the very basic example, which you say is too simple, of Benny and Ayala. What really happens here? She's simply standing on a ladder and signaling him something. Yet, because she's in different location in the gravitational potential, then we're seeing this redshift effect. And again, when you think of it more closely, this is a direct consequence of this equivalence principle. Of the fact that
It makes more sense if they accelerate at rates similar to the speed of light, because then there will be a lag. Okay.
No,
I think.
acceleration. They don't mix acceleration and speed, right? These
Yeah.
are different physical quantities. There is an acceleration and there is a velocity, and these are not the same thing, right?
Yeah.
What she really is, the correct way to think of it is that, right? She has a freely falling, she can define a freely falling coordinate system, and Ayala and Benny also can define a freely falling coordinate system, but it's not the same freely falling coordinate system because they are in a different locations inside the gravitational potential.
Okay.
Okay. Of course, if they were exactly in the same location, then there would not be any difference. But it's not. It's because they're in different locations inside the gravitational potential.
Okay, I got that.
All right. Do you have any further questions? Okay. I will post today my lecture notes on special relativity and also the next problem set. Then again, I do not know when we're going to meet again because that we have to wait and see what the instructions we're going to get. Again, I am following the university rules. I am thinking at the moment we'll have to squeeze a few extra lectures. So I'm thinking at the moment of where we're going to do that. When, not where. I do not want, I prefer to do it earlier than later, but of course I'm not going to do it during the holiday. And I'm not going to do it during the examination period, such as to disturb your ideal as much as possible preparation for the examination. But then again, it means that in a few weeks we'll have to squeeze down 3 lectures, which again, by now, as I said, I mean, I've seen that some of the people who were here in the first lecture are not here anymore. I don't know if this is local or global, or if they're planning to come back or not. But you see what I meant in the first lecture, that I told you that you have to follow very, very closely what I'm saying, because otherwise it's going to be very difficult. We are going to get deeper into the math. It's going to get even more confusing. But hopefully you start to see that at the end, everything makes perfect sense. There is only one way to do these things properly. And the math really just guides us to do what we're doing. There is really no other alternative way of doing that, and that's part of the beauty. And you see that once you cross through that, then your understanding of not only of that physics we're doing here, but of the generally in physics that you're learning, I think is going to be considerably benefit and you're going to considerably deepen your understanding. So I think it's definitely worth the effort. But that's up to you. You do have to work hard in this course. I told you that. Any last questions? No. Then I wish you a happy Passover, safe and quiet, and good luck. And I'll see you, I'm not sure exactly when, you'll get a notification from me. If you don't hear anything, that means that we're just following whatever you get the notifications from Yossi and from the university authorities. If there is something I want to change, then I will send a notification to all of you. So good luck in your studies. Use the time. I'm available at least via mail. You can always send me questions. Use the time to make sure that everything is clear in your mind, because after Passover holiday, we're going to get into a more confusing math. So make sure that everything we said so far is clear in your mind before we're going to get even deeper into confusing things. All right.
Thank you.
Good use of your time, and see you all in after the holiday, after Passover holiday.
Thank you.
All right. Bye-bye. Except you are on that I'm going to see you before, I guess.